Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, doctor. So this is a video about to answer the lab questions. So first of all, let's explain the code for this part. So I import a standard data science library. I use linear SVC for skitlearn because is it efficient for binary classification tasks like this and the standard scalars because SVMs require normalized data? Next, we go for the data loading and preparation. So I separate the features from the target variable. So I explicitly drop the patient ID because it is just an index and has no medical relevance to the diabetic predictions. Next, we go for the splitting the data. This ensures that if 30% of patients are diabetic in the total data, so 30% are also diabetic in the test set. So what it does is divide the data into a training set to teach the model and a testing set to evaluate it. For further explanations, I split the data into the 67 training and 33% testing. So gradually, I use stratify equal to y. Since our dataset is small, stratification ensures that the proportion of the diabetic to non-diabetic patient remains balanced in both sets, so it prevents a biased evaluation. So next we go for the scaling. So what it does, it transforms the data so every feature has a mean of 0 and a standard deviations of 1. So I apply standard scalar here to normalize the features. This is a critical step for support vector machines. Without scaling, feature with large number like glucose level of 150 zeros will dominate features with small numbers like pregnancies 1 to 5, causing the models to learn incorrectly. Next, we go to the model training. So dot fit here command is the actual learning process where the model finds the baseline hyperplane to separate the classes. So I train the linear SVC model on the scale the training data. I set a random underscore stat equal to 42 to ensure my results are reproducible every time the code is run. Next, for the plotting, for the first plot for is the confusion metric. So what it does here, it predicts label for the hidden data set and compare them to the actual answers. So to evaluate the performance, I generate a confusion metric. This heat map, I use a heat map here, allow us to visualize not just the accuracy, but specifically where the model makes mistakes, distinguishes between false positive and a false negative. Next, for the second plot, so it does the extract the weight. For example, the CLF.COF here is the model assigned to each features. So since this is a linear model, I can extract the coefficients to interpret the model. This bar chart shows features carry the most weight. A higher absolute value means the feature is a stronger predictor of a diabetic risk. Next, plot is for the decision boundaries. Since we cannot draw a five-dimensional graph 5D graph, we simplify the problem to two dimensions with age versus BMI. To visualize how the math works, we create a grid of thousands of dots uh, for the NP dot mesh grid. Predict the color for every dot and draw the background. Here, color. So I want to visualize the decision boundaries, the actual lines the model draw to separate patients. Since I cannot plot 5D, I restrained a simplified model using only the top two features, age and BMI. The red and blue region show the model risk zones, and the dots represent our actual patient data. Next, we go to the result. So this is the result how after we run the code here. If you look at the first graph on the left, this is a confusion metric. This evaluates how well the model performed on the test data. The diagonal values represent the correct prediction, where the model correctly identified non-diabetic and diabetic patients. So the off diagonal value shows the errors. In this run, we can see the model is generally accurate. Too, with a small dataset, every misclassification is noticeable. Moving to the middle graph, I analyze the feature coefficients. This answers the question which medical factor matter most. So the bar chart ranks the features by their influence. My analysis shows that age and BMI are the most significant predictor. The large positive bar indicate that at age and BMI increase, the risk of the diabetes increase significantly according to this model. Finally, the graph on the right visualizes the decision boundary. So this is a 2D screen because we can only create two from the features. So the line you see here is the hyperplane created by the linear SVC. So it clearly separates the high risk zone in red from the low risk zone in the blue. So you can see how the model attempts to draw a straight line to separate the actual patient data point. So in conclusion, the linear SVC model was successfully trained to identify diabetes risks. It not only provide prediction but also offer interpretable insight, confirming that the age and BMI are critical risk factor in this specific data set. I think that's all from me. Thank you for listening.